I have mentioned here what is the effect of microsegregation. Why are we really so much concerned about microsegregation during solidification? What are its actual impact on quality? Let us try to understand. On a micro scale, that means on a scale of say few microns when solidification is taking place, that means I have told you the solidification is taking place through dendrites, formation of dendrites. So, what are the within a dendrite distance? So, it may be say 20 micron, 30 micron, 40 micron, 50 micron. So, on a micro scale, this partitioning or segregation of solutes, all solutes, all soluble elements or alloying elements from solidifying dendrites to adjacent liquid, it continues throughout the casting process. Please try to remember this. Whenever there is a solidification, there is a segregation. So, this is taking place throughout the solidification or casting process. So, the solutes, they are segregating from the liquid to the solid, just the reverse, from the solid to the liquid. That means, they are becoming more and more rich in the liquid. The solids are becoming relatively less rich in these alloying elements. Liquid is becoming more rich. So, the dendrites are relatively less in concentration of the alloying elements. The liquid, which is yet to be solidified, is becoming more and more rich. So, the adjacent liquid is becoming more rich. This continues throughout the solidification process. So, we call it microsegregation of solutes from solidifying dendrites to adjacent liquid. Now, as I was telling you, lower values of this partition coefficient K, what implication does it have? And if the diffusion coefficient in solid is low, then what happens? Then, as I was discussing from this relation, look at the figures. If you have small k, that means k almost coming towards 0, that means less than 1, k is always less than 1, I have told you, but lower the value of k, you have mode of segregation. Again, here this A is a back diffusion parameter, it is directly dependent on the diffusion coefficient ds in the solid for a particular element. So, if A and ds they are low, then Cl is also relatively high. So, please try to remember what is happening. Small k means high Cl, small a means small d. So, d smaller the d value, lower will be the a value. So, smaller a value because of the smaller d value again will increase Cl. So, segregation, the amount of alloying elements in the liquid, final liquid which is getting solidified, is becoming more high, more rich when K is very low and the diffusivity of that particular element is relatively low in solid. So, these are the two important things. Again, so what I have told, lower values of this partition coefficient K and lower value of the diffusion coefficient in solid ds for an alloying element result in higher enrichment of that particular element, alloying element. Consequently, what is happening? The value of actual solidus, because this actual solidus depends on what? What will solidify? The last liquid which will remain, that is solidifying finally. So, the concentration of that liquid is which is becoming more and more rich in all the alloying elements. So, more is the enrichment, more is the segregation, more is the enrichment, lower will be the TSA because of the enrichment. So, this TSA, that means actual solidus, comes down from the equilibrium solidus TAC. So, what we find through iron carbon diagram or any phase diagram, in fact iron silicon or iron manganese, any phase diagram, what we get is TAC, the equilibrium solidus but what is important is the actual solidus. So, you try to understand what is happening. Microsegregation is resulting in higher enrichment compared to the C0 value. Cl is increasing, the concentration of all alloying elements in the last liquid which is solidifying is more compared to the original concentration in the particular grade. So, the final liquid which is solidifying has a much lower temperature. So, the solidus is increasing, that particular solid which is solidifying is more rich in the alloying elements. So, the last area which is solidifying, which is heavily segregated, that means the concentration of all alloying elements in that area is relatively more compared to an area which is solidified during the early stage of solidification. So, please try to remember the two important implications. First, during solidification, segregation is taking place. So, on a micro scale, this partitioning of segregation of solutes is segregating from where? From the solidifying dendrite to adjacent liquid. So, this takes place throughout the solidification process. So, because of that, what is happening? Lower is the value of K and lower is the diffusion coefficient of that particular element in the solid, which is, we call it back diffusion. Because of that, because of these two lower values, Cl is increasing, that means segregation is more, and more is the segregation, the actual solidus becomes low because of this segregation. So, the difference between TAC and TSA, that means the equilibrium solidus and the actual solidus, becomes more. Actual solidus is much lower compared to the equilibrium solidus. So, what is happening? This is decreasing, this is more or less constant. So, the actual temperature range of solidification, which is supposed to be TL minus TAC theoretically, but actually it is TL, that means liquidus minus actual solidus. So, this temperature differential is also increasing because of microsegregation. So, two things are happening. The last solid which is solidifying towards the end of solidification is more rich in all the alloying elements. So, we call it central segregation. Any central area of any casting has to be rich in all alloying elements, whatever alloying elements are present in the particular steel grade. So, all are causing microsegregation. It is a question of degree. Some are causing more microsegregation, some are causing less. If the value of K, that means the distribution coefficient, is relatively less, all are less than 1, but for certain alloying elements I will come to it, like phosphorus, sulfur, for these elements these K values are relatively low, much low compared to say manganese, silicon, all these alloying elements. So, what happens is more segregation is created by phosphorus and sulfur, and what is the other issue? The solidus is suppressed from the equilibrium solidus. So, that temperature range of solidification TL minus actual solidus, this difference is also increasing. So, because of that temperature interval is increasing. So, temperature interval increasing means what happens? Actual depth of mushy zone is increasing, and the actual thickness of the solid shell during solidification is relatively low and the mushy zone is more. Yeah, look at this figure here. This I have discussed earlier. During the stage of solidification, that means when solidification is underway, it is not complete, what we have? We have a portion of the solid which has already become solid, that means during solidification. There is of course liquid, because solidification is not yet complete, and in between the liquid and the solid shell there is a mushy zone which is a combination of dendrites and liquid. So, this area is solidified, totally solidified. So, the solid fraction here is 1, mushy zone start, that means liquid, at the interface between the liquid and the mushy zone, solid fraction is 0. So, here solid fraction is increasing from 0 it is increasing towards 1 as we are going to the solid totally solidified area zone. So, it is the solid zone, there is a mushy zone, that is liquid plus solid, and this is liquid. So, the solid fraction is 0 here, the solid fraction is 1 here, it is 0%, is 100%. In between you have a mixture of solid and liquid. So, the mushy zone is determined by how much will be the width depth of mushy zone, what will be the depth of solid phase during solidification depends on, if you look at this figure, this is the thickness. So, the actual solid, the depth of solid, it depends on what? Depends on, look at here, what is the temperature here? Corresponding temperature, look at the temperature here. This is depends on here, this is the temperature. So, this is depends on the actual, this is the actual, corresponds to the actual solidus temperature. So, the thickness depends on the actual solidus temperature, which is TSA. The liquidus point corresponds to, this is the liquidus point, this for any section AB I am talking about. This is the liquidus, that means the depth of mushy zone depth depends on this, and this is equivalent to, proportional to the temperature range of solidification, that means the difference between TL liquidus and TSA, the actual solidus. So, the mode is segregation, means the actual solidus is suppressed. So, TSA is suppressed. So, if TSA is suppressed means this temperature becomes lower. So, TL is more or less fixed, mode the segregation means TSA is coming down. If TSA coming down means T0 is the temperature, surface temperature of the solid. So, let us assume during cooling it is more or less constant. So, if TSA is suppressed means SA, the thickness of the solid shell also comes down, because solid shell thickness is proportional to the temperature difference between the actual solidus and the surface temperature of the solid, and the mushy zone depth is proportional to the temperature of solidification, the temperature difference of solidification, that means the difference between the liquidus and the actual solidus. Since segregation is suppressing this, is bringing down this actual solidus, TL, that means the liquid is more or less constant, T0 is more or less constant. So, what is happening? During segregation, if TSA is suppressed, TSA comes down, so difference between liquidus and actual solidus increases. This difference increases. This difference increases means the mushy zone depth, SA, SL minus SA, this depth also will increase. So, the mushy zone depth will increase, and the solid shell thickness, this is coming down, because T0 is constant, TSA is coming down, means it is becoming near and almost near to T0, that means this difference is also coming down. This difference is increasing, TL minus TSA is increasing. So, solidification temperature range is increasing. So, the mushy zone depth is increasing, but you see here TSA coming down means TSA minus T0. This difference, temperature difference is decreasing. This temperature difference decreases means this SA will also decrease. So, what are the implications of segregation? One is the last solidification which is taking place, the last area of the solid is definitely more rich in all alloying elements. It is a question of relatively, whether how low is the K value, how low is the diffusivity in solid. If both these two are very low, that means it will increase, the segregation will increase. Segregation increases means the particular area which is solidified at the last is more rich. Number one, from the chemistry point of view, from the temperature point of view, the actual solidus, because of more segregation, is suppressed from the equilibrium solidus. So, the actual solidus comes down So, the temperature difference between the liquidus and the actual solidus increases. So, the mushy zone becomes quite wide and the actual solid depth becomes less narrow. So, during solidification, when there is too much of segregation, what is evident is the mushy zone, that is a big mushy zone, deep mushy zone, and the actual solid shell is narrow. So, this has implication on the strength of the strand, because a strand consists of solid and liquid during solidification. So, during solidification, the strength of the strand is determined by how much of solid is there, how much of liquid is there. So, if the solid shell is relatively thin and the mushy zone is relatively more, the strength of the shell also will be relatively less. So, this we will be discussing later on, but what is important to know that because of the suppression of the actual solidus owing to segregation, the depth of mushy zone increases and the thickness of solid shell decreases. This is important to remember. Now, as I was telling you, because of this microsegregation, what is happening? Higher actual depth of mushy zone, solid plus liquid zone is more, actual thickness of solid shell is less. This is a consequence of segregation, which is contributed by all alloying elements. Question of more or less, depending on what is the K value. Well, smaller is the K value, more is the segregation. This, please try to remember, this will be of immense consequence in identifying what are the factors causing crack formation at different stage of solidification, different stage of cooling. Now, as I was telling you, partition coefficient between solid and liquid, that means this K value, which is less than 1 for all alloying elements, is a question of how low is K, but K is always less than 1. Now, look at the K values for 4 common alloying elements. So, manganese, silicon, when solidification is taking place through delta ferrite initial solid, it is 0.76, 0.76, 0.77 for silicon. Look at the value of for gamma when solidification takes place through gamma is 0.78, 0.52 silicon. So, look at now the values for phosphorus and sulfur. 0.23 this delta, sulfur 0.05, gamma for gamma solidification, small value of this value of small k is very low, 0.13. For sulfur it is much still lower, 0.35. So, what is important to understand is between alloying elements, if you compare alloying elements say manganese silicon and phosphorus sulfur has much less value of K, more low value of K compared to manganese silicon. This is first point to remember. So, phosphorus and sulfur are more potent for causing microsegregation. This is first thing to remember compared to manganese silicon. These values are not very low, okay, but phosphorus sulfurs, the value K values are quite low, and number 1. Number 2, between delta and gamma, the phosphorus and sulfur they segregate more when the solidification mode is austenite, that means gamma. That means when carbon equivalent is more than 0.5, that means when solidification is taking place through austenite, then you have relatively more segregation than for a very low carbon steel where the carbon is less than 0.1, say 0.07, 0.05 carbon. Any steel which is having very low carbon segregation, the solidification is through delta, and relatively between delta and gamma, gamma is less in the K value, small k value, the partition coefficient for phosphorus sulfur. This is for gamma, it is relatively more. So, here for delta it is relatively high, that means segregation is very high in gamma solidification. As such, for phosphorus and sulfur it is high compared to manganese silicon, but between delta and gamma solidification, for gamma solidification, that means austenitic solidification, phosphorus values are still lower. So, what is important is phosphorus and sulfur, for phosphorus and sulfur microsegregation is very high. So, the actual solidus is much lower compared to the equilibrium solidus. So, more is the microsegregation, as I have told you, lower will be the value of actual solidus, because it is suppressed more, it comes down relatively more compared to the equilibrium value because of microsegregation. So, microsegregation results in heavy, first microsegregation of phosphorus and sulfur causes very high level of partition, because the K values are relatively low when solidification takes place through austenitic mode, and because of this high segregation, high amount of segregation means more amount of segregation for phosphorus and sulfur in austenitic mode, the value of solidus, actual value of solidus is much lower compared to the equilibrium solidus. And what is happening is, when the last solid which is solidifying, that means the central area of the cast structure is having high level of segregation. Now, this is called central segregation. This segregated low melting liquid, they gets transferred during the stage of solidification more towards the center, and the central segregation is more rich with alloying elements. So, this is called central segregation. If you measure the concentration of the alloying elements at the center and at the areas which have solidified earlier, you will find always the central portion of the cast is having more of these alloying elements. So, this segregated low melting liquid causes central segregation, and the actual solidus is also suppressed, becomes much lower. Now, what is important to understand is that all of us know that we want to add some amount of manganese in steel to take care of the deleterious effect of sulfur. So, when the ratio of manganese by sulfur is more than 25, we find that this deleterious effect of sulfur in causing microsegregation is relatively less. Why is it so? If you do not have sufficient manganese, then what happens? Sulfur will combine with iron to form iron sulfide, whose melting point is relatively lower. So, to take care of that, if you have some manganese in steel, so preferentially sulfur will combine with manganese rather than iron, and the manganese sulfide temperature of that, melting point of that is relatively higher compared to iron sulfide. So, we do not have iron sulfide in steel. So, the relatively bad effect of sulfur is taken care of if you have high manganese by sulfur ratio in steel. That is why you must have manganese by sulfur ratio more than 25. That means, if you have say 0.1 sulfur in steel, our manganese has to be minimum 0.25. If you have 0.2 sulfur, manganese has to be more than 0.5 in the steel. This is from the point of view of taking care of the deleterious effect of sulfur in causing high level of segregation, in causing incipient fusion, in causing low melting constituent of iron sulfide. These have to be taken care of by putting more amount of manganese in the relatively more amount of manganese in steel. But for sulfur there is a savior called manganese, but for phosphorus there is no savior. We do not know of any alloying element which will combine with phosphorus and will not create iron phosphide. So, manganese forms manganese sulfide, it does not allow sulfur to form iron sulfide, but there is no alloying element which can prevent phosphorus from forming iron phosphide, which like iron sulfide is also a low melting constituent and is a cause of concern for segregation and suppression of actual solidus. So, what is important to remember is that phosphorus, sulfur, they are more potent for causing microsegregation, more potent for suppression of actual solidus compared to the liquidus. So, the difference between liquidus and actual solidus increases. So, what is the consequence of this? The relative depth of mushy zone is more and the thickness of solid shell is less during solidification, the process of solidification. So, the strength of the strand will be less because we have more of liquid and less of solid. So, the consequence of microsegregation is twofold. First, the last area which is solidifying is heavily segregated. That area has more of the segregating elements, so relatively impure. That is one, we call it central segregation. Second, the actual solidus is much less compared to the equilibrium solidus because of segregation. And I have also mentioned that phosphorus and sulfur are more potent segregating solutes, segregating elements compared to other alloying elements like manganese, silicon, chromium, nickel. So, this phosphorus and sulfur we have to be very careful so that they do not create segregation. So, we have to be very, very careful. So, carbon also, this K values are also less in for carbon, but for the carbon what happens is the back diffusivity ds for carbon, for nitrogen, all these interstitial elements, it is much higher, they diffuse fast. So, even if there is a segregation during the stage of solidification because of diffusion, the level of segregation comes down, which does not happen for phosphorus sulfur. Here the K values are low, diffusivity also are relatively low. Since I have discussed beforehand that when K values are low and the diffusibility are low, diffusivity of that particular element in solid is low, we have high amount of segregation. So, phosphorus and sulfur are two elements which have small k and also small diffusivity, and that creates very high amount of segregation. Thank you very much.